So yeah, thank you for coming to my talk today. So today I'm just going to be talking about kind of a chemistry application in generating approximate ground states of molecules using quantum machine learning. Yeah, just wanted to get started then. So just kind of a quick roadmap of what I'm going to talk about in this talk. Just intro to quantum chemistry, not going to spend too much time on it since we've kind of discussed it already today. Our model that we talked about, so what we're going to do is we're trying to use Wavefunction, so like the ground state of a molecule, as quantum data in a quantum machine learning problem. So kind of, essentially we want to see, okay, well, how well does this work for some very small molecular systems in a very ideal case? We're not necessarily going to be looking, there's some ideas that could apply to NISQ things, but this material wasn't really done with NISQ in mind from the outset, so just keep that in mind. Some things that we did find were we were able to prove some limitations on what you can learn in this situation for these type of models, and then kind of want to open it to, there's a lot of different directions this work could take, and some open questions regarding that. So, okay, great. So of course, as we've kind of heard already, why do we want to simulate chemistry? Well, one is how to predict reaction rates, chemical reaction rates. And typically, right, this is in drug design, catalysis, material synthesis. This is a very important property. And primarily this is investigated, again, through the ground state problem. Sorry, there we go. As we've discussed, right, the ground state problems, this has had a lot of work in classical theory and also in quantum simulation as well. But I kind of wanted to discuss why do we actually care about the ground state problem in some of the larger context. I think Nick discussed this a little bit earlier, talking about some of the specific applications. But yeah, let's get into this. So, okay, as we know, the quantum chemistry model, typically what we're doing is we assume we have a classical nuclei, which are just point charges in space, and then the electrons are treated quantum mechanically with some atomic orbitals. So, I mean, you can either do plane waves in a box, or typically they're 3D Gaussian basis functions. Okay, so, right, the ground state electronic structure problem is given this Hamiltonian of 1 and 2 body interactions in the electronic structure problem, we want to find the lowest eigenvalue, right? So specifically though, things that are not as, or it's not talked about as much as that, right, for a lot of different problems, when we want to compute different, or compute reaction rates, is we actually want the ground state at different nuclear positions. So we have a family of Hamiltonians that are actually parameterized by R here. In R, in this case, is the vector of the Cartesian coordinates of all the different nuclear positions. So if you had 2 nuclei, you'd have to have 6 numbers representing where they are in 3D space. So it's not just one ground state we need a family of ground states to compare energies, right? We don't necessarily care about just the ground state energy as is. Doesn't really tell us anything unless we're comparing it to another value. All right, yeah, so I touched on this a little bit. The family of ground states we need, right, kind of in this 2D map. So this is like the degree of rotation of this axis here on this 4-atom molecule, this nitrate ion. Basically, every point on this topography is a ground state calculation, right? So we'd actually need, in order to compare the energy, like let's say right here at this minima and the one of this deeper minima over here, a priori, we don't know like what's the shortest path or the paths with the smallest transition energy here. Right, so, excuse me. So one of the things to think about, right, is that even if we did have a fault-tolerant computer, or a fault-tolerant quantum computer, we'd have to, and we're able to run like quantum phase estimation and get correct ground states easily. We'd have to do it naively. We'd have to compute it at every one of these points, or at least with some discretization. And so that's a very large overhead that we'd maybe we don't have to do as naively. Maybe this is something we can learn if we just sample, sparsely around this. Okay, so yeah, again, right, this is just a 2D example, but really this is a higher dimensional object. It's, like 3 Cartesian coordinates per atom. And of course, as we've kind of already discussed, we do need these energies to be highly accurate because to compute reaction rates, they're in an exponential function. So that's why we require this thing called chemical accuracy. Okay, so as I was just kind of explaining at the end of the last slide, right, we need to sample we need a ground state energy at each point if we want to compute this reaction rate. And we need to know, we don't even know where the local minima are in different transition states of things of that sort. So like this kind of whole topography, the thing we call the potential energy surface, is something that's not known with high accuracy beforehand. So again, right, like even if we were able to compute it, we'd have to compute a lot of different points, a lot of different phase estimations with a lot of different Hamiltonians. So, okay, the idea is that I kind of already alluded to this, but instead of using it to compute the ground state over and over again on the potential energy surface, we want to utilize wave functions like sparsely sampled on the PES as quantum data for a QML problem. All right, so what do I mean by a generative QML model? So sometimes you might have seen this before, this quantum machine learning so-called Punnett square, where you're looking at the type of algorithm versus the type of data you care about. So in this case, I really think we're squarely in this QQ regime. So what we mean is the data that we want to learn with is the actual ground state wave function, if we're able to get that. That's the data, and learn to predict the wave function or a preparation of it at another state that wasn't in the training set. And of course, doing this with a quantum algorithm to simulate the physics. So we're squarely in this QQ regime. So, all right, this is kind of a high-level overview of what we're thinking. So you have some input molecule that's parameterized by where the nuclear positions are. You have a number of basis functions that represent it and a number of electrons. What you normally do is compute the coefficients of the Hamiltonian with your favorite quantum chemistry package. You'd then feed this, of course, into a compiler. Let's say for phase estimation, this would be all the gates needed to do the e to the IH of R times T, and hopefully extract ground state energy with some initial overlap, as was mentioned a few times before as well. So yeah, that's right. The main routine, molecule, you compute the Hamiltonian, which is classically efficient. Then you choose some simulation and rotate your initial guess state into a final state. So since we have this family of Hamiltonians over R, maybe what we can do is if we fix, right, a sequence of unitaries, we can maybe learn these thetas directly and generalize over the R input over a few pieces of quantum data, which is the ground state. Right, so something like a neural network directly has the input is just the nuclear coordinates in the definition of the system we care about, and then it outputs thetas to some fixed circuit. So that's kind of the idea we're going to run with here. And I'll be a little bit more specific in a second. And as I alluded to, so there's some big assumptions here. The first one's not so bad, right? So the initial state is easy to prepare. In a lot of cases, it's an assumption, but we expect the overlap of the initial state to have some constant, there's some constant overlap with the true ground state. And one of the biggest assumptions here, right, of course, is that we're saying, oh, we have access to a few ground states for the training data. That, of course, is a big assumption because we know we can't necessarily prepare these in general. But the idea here was more of a proof of concept to see, well, if we can generalize really well with only a few exact ground states, that's motivation to move this project forward where we have imperfect preparations of the ground state and see how much noise affects that. So that would be something of future work. But really, we just want to see how well does it work in the most ideal case? Can we actually learn elsewhere on the potential, extrapolate elsewhere? Okay, so here's kind of a more specific schematic of what we're doing. Right, so we have the definition of our molecule, which has nuclear coordinates. That's fed into a classical neural network, which outputs thetas for a fixed unitary here. So this unitary, of course, is just called UNN in general, but in many cases, you want this to be probably close to the problem, physically inspired by, in our case, it's singles and doubles Givens rotations on the molecular space here. So we know that preparing the mean field state is simple. So the initial state here, right? We have a register that holds it for the ith nuclear configuration. And of course, this we also prepare this again on another register. This would be the ground state prep, right? This is the large assumption that we're able to actually prepare this true psi naught at Ri. But the idea here is that, well, if we choose a cost function and we can evaluate the gradients efficiently given this setup here, then essentially all we have to do is go back and update the classical neural network to output new thetas and iterate there until we get learning a general function of psi naught tilde over the select r's that we chose. So at the end, what we get is that, well, if we want a new molecule that wasn't in the data set, we just input the new coordinates, right? We cheaply generate a bunch of thetas for this, and we're able to rotate the mean field state into an approximate ground state. So this is the key point right here. Yeah, if there's any questions at this point, that's probably a good place. All right. Cool. So yeah, again, this is the main concept here is that we're saving, if we're able to actually learn this representation with this setup here, the classical neural network, the quantum circuit, then we wouldn't have to run our simulation algorithm over and over again. We could just generate the new thetas. So what do we actually do? We just used a very simple cost function. This is just average fidelity. So in this case, this is like the approximate psi tilde with using the neural network parameters to, so this is the approximate side, this is the true side. Again, it's just an average over the n different samples we took of those ground states. We also found that the gradient evaluation is efficient, and we looked at either doing it term by term for each of those gamma parameters in the classical neural network by using the Hadamard test, or coherently is possible as well. Of course, that's more in the fault-tolerant regime. So yeah, this is very simple cost function. Can evaluate the gradient efficiently. This is not as important, but this is just the specific informal theorem for the Hadamard test method. So it just has to do with how many samples we have and the max value of the gradient of the classical neural network. So yeah, all right, great. So the key points again are that, right, we want to learn the wave function itself, or at least some approximate representation of it, so that we can probe the system later with any observable we want, not necessarily just the energy. And of course, also, we found, of course, that there's an efficient gradient evaluation that we can do that's theoretically tractable in a sense. Okay, so how well does this work? So essentially what we did was test this on a few examples of toy model systems in chemistry. And yeah, so we use the Jordan-Wigner mapping. So 1 qubit is 1 spin orbital. That's the assumption we're making through this, and use some very minimal basis for these molecules, and fix some ansatz dependent on given rotations that look like this, the singles and doubles rotations. Anyways, so the interesting thing here, all right, so first is this H4 rectangular stretch. So H4 is kind of this toy strongly correlated model that shows up in chemistry. So strongly correlated meaning that there's a bunch of different electronic configurations that are close together that are needed to represent the ground state. And it's not just dominated by one single configuration. So typically it's a hard problem to accurately get. So, okay, so the first thing we did on the left here is the energy. So this is the energy of the system. Red is the actual model that we found, or that we developed. The teal is the true ground state energy at all of these points along here. And that this is just, again, stretching these atoms like this in a rectangular fashion. Blue is the mean field state if you were just to use the classically efficient and like Hartree-Fock state to compute the energy. See, it's squarely above the true ground state for most of this. But I guess the interesting thing, right, is that each one of these dots, right, so we've used only 5 ground states at each of these R values. So 1 here, and then the 3 others over here. So that's all we use for training this classical neural network. We can see that already. What's kind of surprising, just by kind of sampling, at the equilibrium geometry, then a few more closer to dissociation, that we're getting pretty good extrapolations past the data set that we wouldn't expect. So what that's telling us is that there's a lot of rich information in the actual wave function as a quantum data object, right? And so on the right-hand side here, this isn't energy anymore, this is fidelity. So this is the model. The teal in this case, sorry, the color is a little bit confusing, but the teal in this case is the ground state wave function overlapped with the model wave function. So you see we have something that's stays fairly high fidelity over this whole bond stretching coordinate. And then the blue one is the mean field state with the true ground state. And of course, it starts to drop off as you pull the bond apart. Okay, so that's pretty interesting, but we're not really getting the correct energy and extrapolating out to pulling the molecule totally apart, right, in the dissociation limit. But just by one idea, of course, is just, well, maybe we don't have enough of this information from the dissociated part, so let's just kind of shift the data points over. So we do that and get, I have no idea why this is 90 degrees rotated, so sorry. Must be the, that's weird. So apologies. But okay, let's look at the left. So on the left, right, we just shifted some of the points over, or added, actually what we did is just add one more point over here into our model, and we get extremely good agreement with some deviation right here at the difficult, kind of like the midway molecular dissociation. But the interesting thing, of course, is that, right, we can extrapolate that there's some dissociation limit, and that, we get this repulsion curve as the atoms get too close together. And that's all just from a few of the wave functions sampled at each of these points, and then training a classical neural network to rotate those thetas the right way. So at each of these new points in the model, this one, right, at each one of these new points, all we're doing is saying, I want the correct unitary to rotate the mean field state at, 6 Bohr, and we can just generate that, right? So that part is surprising that with such few points, it was able to do this. Okay, so of course, that's just a 1D case. And while this is a really simple system, it was just to give you an idea of in 2 dimensions, we get similar quality results. So just kind of looking at the right-hand graph here, this is, again, just 6 points where angle is the y-axis here, this theta h, and distance, symmetric distance is this delta h here. And we only do 6, and I mean, most of this map is almost fidelity of 1 for the other states that we sampled. Or sorry, for the data that's generated that wasn't in the training set, with some loss of fidelity over here. But of course, if we just add, you know, a few more points, we get pretty high fidelity overall. So again, it's kind of the same story, though this system is pretty small. So the H4 one is maybe more representative. But still, we see that, at least for the 1 and 2D toy model cases that we looked at, we really got a lot of information from just a few ground states. That's kind of the main takeaway. So I'll shift gears like a little bit. We have some theoretical results in this work about the limitations on learning. And I'll go into one example of that. So kind of the idea was that naturally, if you sample from one region of a potential energy surface, can we bound how much we can learn somewhere else farther away? That's the idea. So one way we tried to investigate this is to look at the adiabatic Grover search problem. So there's this paper from 2002 from Rowland and Cerf that maps the unstructured search problem onto an adiabatic time evolution problem. So essentially what you get is this Hamiltonian that's parameterized by S, where S is the reduced time. This unfortunately got messed up by the upload. So sorry, but this is H0 is a projector onto the superposition of all bit strings. So 1 minus that projector, and HM is the projector onto the selected M state that you're searching for. So yeah, apologies that can't really read this, but yeah, this should be 1 minus ket M bra M, and then 1 minus ket psi naught bra psi naught. Okay, so anyway, you have this interpolated Hamiltonian that goes from, you're starting in the state here, right, the superposition of all bit strings, and then slowly time evolving over to the state M. And so what they found is that they found an optimal evolution time, which is square rooted n, right, reproducing that quadratic speed up that you see. So that this is optimal. But the idea here is that, well, maybe we can use some of this tool, some of this tool that I developed, right, to what if we only evolve to points here and use these as samples before this S star coordinate and try to see what are the limits on us learning M from just points on this left-hand side. So yeah, with that, just like a summary of the theorem, because it's pretty long, but we first find a correspondence between the fermionic Hamiltonian and the Grover Hamiltonian. We map the reduced time parameter, this S, to some arbitrary parameter like the coordinate, right, like the bond coordinate. And, oh, sorry, yeah. But anyway, so what we can do is limit the sample region, like I said before, S star, and this threshold ensures that there's, basically we prove by contradiction that there's no algorithm that can learn M with a number of wave function data samples that requires less than O root n queries to the Hamiltonian. So this is kind of a worst case scenario in chemistry, right? Like this gap is a function of, right, this has exponentially small overlap with increasing number of n bit strings, but it has to follow this lower bound. So the intuition you should get from this, of course, is that if we have like a ground state and excited state potential energy surface that have a really small gap, naturally it's going to be harder to learn through the gap if it's confined to this one dimension. Now, in general, right, you could imagine this expanded into 2 dimensions, and if you take a path that kind of goes around the edge with a larger gap in that, so it looks like 2 parabolas, right? So like one curving down, one like this. If you take a path that's around it, you won't be restricted just by that minimum gap in that 2D space. So really, this is kind of like a worst case scenario of what you can learn. So the takeaway, of course, is that naturally there's no universal exponential speedup allowed to just learn across the potential energy surface anywhere. And algorithms that we can learn from or algorithms that can learn that unknown state somewhere else in the potential energy surface have to satisfy these lower bounds on query complexity for the unstructured search problem. And yeah, so sampling states on, like more sparse, like if we sample farther away at larger R's, naturally gives us a better generalization of the whole surface, kind of as expected. So some open questions, future directions. So looking back at kind of the setup of this model, of course, what we want to look at is how do errors in the ground state prep, right? If we just have some constant overlap, how does that affect the actual output quality for the approximate ground states? Is there any viability here for state prep routines in NISQ? I don't know. What type of, like, we just used a really simple feed-forward classical neural network. There's lots of different architectures, of course. Like, is there any ideal choice there? Is there a better way to generate the quantum neural network part that doesn't require us kind of selecting these Givens rotations somewhat arbitrarily? And what's the interplay between these two, right? This is quite unexplored. Also would, instead of just using the mean field state and rotating that to our hopefully the ground state, would a higher quality classical input with higher overlap always be preferable? Or is that just extra overhead that we don't need? And of course, we only really looked at 1 and 2 dimensions, but in general, R for large molecules is going to be some very high dimensional objects. So does this still perform as R scales up? And of course, too, we use a very simple fidelity cost function on average. And that's only one we explored so far. So there's other choices that can be done there as well. All right, so some conclusions. The general architecture and cost function we think is promising, but again, this is kind of a proof of concept, and there's a lot of stuff we need to still learn about this. Again, as I reiterated on the last slide, the high dimensional PES could still be a problem, and we don't know. But one of the big takeaways, I think, is that at least just a few points of these quantum data as the ground state wave function seems to be quite information rich for extrapolating to other parts of the potential energy surface. And I think that was somewhat surprising how well it did. But of course, for practical applications, we're going to have to see how noise affects this, or how imperfect quantum data actually, at what point does it ruin the model? Yeah, with that, just want to acknowledge my co-authors, and then, of course, Brigitte Whaley and Umesh to hosting me as a postdoc here at the Simons Institute. And thank you all for your attention. Yeah.
Is there some way to quantify the quantum machine learning protocol here, or can you be outputting something that's tractable like RDMs and then
That's
predict couple cluster amplitudes?
I actually thought, in general, this doesn't have to be on a QPU, right? You could do exactly what you're saying. And I I've thought about it, but I haven't like implemented anything in terms of classical methods, though I think it would be just for classical ML for chemistry would be a nice target, like a nice way to think about this problem. Yep.
So on your cost function, you explicitly involve these multiple overlap in the wave functions.
Yeah.
So if I had a wave function in a n-dimensional space, what would be the time required to spin? How would that scale there?
Let's see. Let me go back here. So on the yeah. So this the fidelity cost function here. So you're saying what would be the time?
The time required to, I mean, because to determine this overlap, you have to do many runs of the experiment, right?
Yes. Mm-hmm.
So for a high-dimensional state, it's going to take a very long time to. I'd imagine for a high-dimensional state, you have to do many experimental runs to converge these multiple overlaps.
Oh yeah. So some of the assumption we're making here, right, is that we're lower bounded by some constant factor overlap even as the size increases, because we can generate the mean field state with decent overlap each time, even as n grows.
Usually, if you have a mean field approximation for like an n-qubit state, doesn't the overlap between the mean field state and the true state that can decay exponentially with n, even though all the expectation values of local observables can be quite close to quite down so long.
So I think this was brought up in Lynn's talk yesterday, is that there's some debate about whether or not the overlap is going to be always some constant factor. But in this work, we're making that assumption because, I mean, in practice, even for like the H4 model function, like the overlap for a lot of these cases was like 50% or greater. And as that happens to be like in doing like classical quantum chemistry, the mean field state is still pretty high overlap even for very large systems. So there's an assumption we're making, which you're catching, which is that we're assuming there's some constant overlap even regardless of the size of the system we care about. But maybe that's not always the case, and that's kind of a debated point currently. But it's just an assumption for our problem. Mm-hmm. Yeah.
The complexity of the gradient, I think it was on like the next slide or something.
Yeah.
It's scaling quadratically with the parameter, right?
With the gamma parameter, yeah. Yeah.
But linearly with the number of nuclei?
Sorry, this n is number of samples, so number of ground states. Yeah.
Just a quick question. I think I probably missed the problem. What's actually how do you parameterize your unitary rotation from the mean field solution to correct ground state?
So you mean like the choice of this unitary? So for this case, what we did was actually I have an extra slide on that one. So we did something that was like adaptive EQE inspired. So for each of these, we initialized the mean field, applied a set of double excitations, basically computed gradients for that operator to some threshold, then did the singles. And so then that was just an ansatz for what we thought the UNN should be. But this is what we did. Yep. Yeah, so then there's product of doubles, then singles to get those two different rotations on the single particle excitations and double particle excitations. Yep.
So you're using the mean field ground state as the initial state.
Yes.
Do you think there could be a more efficient choice for the initial state that maybe one of the ground state for a particular point in a time space, for example?
Yeah, so I think, that was one of my questions too. I mean, I think it's a good question. It's would a higher quality classical input, like if I just had a better than mean field, but still something classically efficient, that obviously gives me a higher overlap, but is that always preferable in practice? I don't know. I mean, it depends on the cost of each one of these things individually, but I think, of course, it would help in the training. Okay, thanks.